A small metal ball is placed on a pair of electrified rails, as seen in this picture. It's in the presence of a magnetic field, so that it's free to roll back and forth. So it's free to sort of move forward and backwards, depending on the forces acting on it. So if the current passing through the metal ball is 90 amperes, find the direction and magnitude of the force on it. Now at first this might seem a bit large, but remember that we actually have quite a short circuit over here. So in reality we might even get less than 90 amps of resistance, but that's what the question is asking us, so we'll use that. Now the first thing to find is the direction, and that should be fairly easy. If we have the current flowing in this direction around the circuit, which we can see from the power supply, then we can just use the right-hand rule in order to figure out the direction of the force. Current moves that way, magnetic field is into the board, so the force will be upward, and the ball will be propelled toward the end of the rails. Right? So what's the magnitude of the force? Well, we have the strength of the magnetic field here, 2 Tesla. This is a fairly strong field, but not the strongest you can get. The distance between the rails is 1 centimeter, so that will be the length of the conductor inside the magnetic field. So if we have our equation, F equals BIL sine theta, we can substitute in some of these numbers. We know that B is 2 Tesla, I is 90 amperes, and L is 1 centimeter. We can see from the direction of the magnetic field that it's going to be perpendicular to the direction of current. So we can ignore the sine theta. It'll just take on its maximum value. Substituting in those numbers, we have 2 Tesla times 90 amperes times 1 centimeter, which gives us 1.8 newtons, and it will be away from the voltage source and toward the end of the rails. So there's our force, 1.8 newtons. Now if the ball weighs 5 grams, find its speed after it has travelled along 70 centimeters of the rails. Now that seems fairly accurate, I think. If we have a 1 centimeter diameter sphere and it's made of metal, then it will tend to have a mass of between 5 and 10 grams. So we can assume that the rails are 70 centimeters long, and during all of this, the ball will experience the acceleration due to this force, right? So now we can use our equations of motion to figure out exactly how fast the ball will end up going. So in this question, we're given a displacement, r, an acceleration we can figure out from our force, and our initial velocity is of course 0. What we're trying to find is v, the velocity of the ball after it's been accelerated over 70 centimeters. So we know that F equals ma. We have the mass, 5 grams, or 5 times 10 to the minus 3 kilograms. And we have the force, so we can calculate acceleration. Substituting in our numbers and rearranging the equation, we have v squared equals 2ar, or taking the square root, v squared equals 2ar. Of course, a is equal to F over m, and you can see I've already made that substitution here. So now, we stick in our numbers. F is going to be 1.8, m is going to be 5 grams, r is going to be 0.7, because we have to measure that in meters. So now our equation looks like this, and of course we can use a calculator to figure out exactly what that value will be. It turns out to be about 22.45 meters per second, which is roughly the speed of a car. So we've actually propelled this little pellet quite fast off the rails. If we used our equations of motion to figure out the time that it would take, it turns out that it would take about a 20th of a second for it to travel this 70 centimeters. Obviously we could increase the speed of the pellet going off the rails simply by increasing the strength of the magnetic field, increasing the current through it, or increasing the distance of the rails. In fact, if we get it fast enough, then we could be firing this little pellet like a bullet from a gun.